of Nawar, and my topic is relaxed fabrication tolerances in rectangular waveguide filters. So I will do a short introduction first, and then I will move to the industrial importance of fabrication tolerances, and then I will discuss a few examples and topologies through which we can achieve robust devices. So the first topology I will discuss is varying height and taper width topology. The second one is a constant width and varying height topology. And the last one is a varying height and varying width topology. So in telecommunication nowadays, we need high data traffic. So in order to address this problem, space industry is moving towards Q and V bands, so which are high frequency bands. So in order to, when we operate at high frequencies, so our filter size decreases. So the fabrication become more significant at higher frequencies. So the dimensions of the filter is very hard to fabricate at such high frequencies. So because the dimensions of the filters are comparable with the fabrication tools, so that's why there are more chances that we will have inaccuracies, and hence filter with more robust fabrication errors are of paramount importance nowadays. So the industrial importance of the filters which are more robust and have a simple topology are that they can be fabricated with a low cost milling process, can be fabricated with a additive manufacturing process, which is a low cost and process, and also we can try other materials like polymers in order to reduce the weight of the device. And if a filter or a device have more fabrication yield, so there are more chances to produce a filter at first shot. So in order um, to save some time and also to reduce the fabrication cost. And with a simple topology, it will take less lead time, so it will also reduce the fabrication cost. So here is a first example with a topology varying height and tapered width topology. So the method was actually based on step-shaped band stop elements and matching networks with optimized height. So the technique was designed to have a wide stop band and also to obtain relaxed filter dimensions. So an example was designed for the frequency specifications here, which where the pass band is between 10.8 to 12.8 gigahertz, and a return loss better than 20 dB, and a stop band between 15.5 to 20 gigahertz with a attenuation level better than 60 dB. Here we can see the schematic of the filter. And once we have the design example, then we can perform the sensitivity analysis in order to check the tolerance analysis of the device. So the dimensions were varied using Gaussian probability function. And the worst case error was equal to plus minus 120 micron. And the number of iterations performed were 100. And the fabrication yield obtained for the device were equal to 94%. So here we can see the sensitivity analysis in this figure. And then the device was fabricated with a 3D printing process, SLA, and material used was black photopolymer resin, and the layer thickness is equal to 25 micron, and the prototype was fabricated in 2 pieces, which can be seen in this photograph. And then the device was assembled with the screws, which can be seen in this photograph. Here is the final response of the device, where we can see that both the simulated response and the measured response are in good match, and all the specifications were achieved. Here we have a second example with varying height and constant width topology. The technique was based on to utilize the first passband replica of the common straight lines. So this technique was successful to achieve filter with more relaxed dimensions, and the filter was then implemented with a SIR structure, which can be seen here. Then a filter was designed for the frequency specifications, where passband was between 37.5 to 42.5 gigahertz, return loss better than 20 dB, and a stop band between 34 to 35. This is the lower stop band, and the upper stop band was between 47 to 50 gigahertz, and attenuation level better than 65 degree. So the design example was then tried to perform the sensitivity analysis, and the dimensions, all the filter dimensions were varied using Gaussian probability function, and the standard deviation value was equal to 10 micron, which corresponds to the worst case error plus minus 25 micron. The number of iterations performed were 200, and the manufacturing yield obtained for the device was 92%. Here we can see the sensitivity analysis of the design. Then the design was fabricated with computer control milling, and the material used was aluminum, and the prototype was fabricated in 2 halves, which can be seen in this photograph. And the final frequency response is here in this figure, where the simulated and measured frequency responses are in good match. Here we have the third example, which we recently published in MWCL with a topology varying height and varying width. The technique was actually based on the same technique which we discussed in the second example, to utilize the first passband replica of the common straight lines. But the novelty in this work is the topology, because here we actually implemented varying width and varying height topology. So how we develop this topology? So initially we designed 2 filters with a constant width, one with a smaller width, and the frequency response of the smaller width is given here in the red curve. And then we designed another filter with a larger width, and the frequency response of the filter is given here in the green curve. And then we concatenated both the structures, and we obtained another response, which is given here in the black with a suppressed low pass response. So this is one advantage of this topology. But then we further exploited this topology to obtain relaxed filter dimensions, which can be seen here in this schematic. So what we did is that we need, in order to enhance the tolerances, we actually increase the width of the smaller sections in order to increase the mechanical gaps. So in that way, we actually obtained filter dimensions which are more relaxed. And then we have one other advantage of this topology was that we obtained the final sections with standard port size. So we actually avoided the tapers which were normally required in these type of filters. So we exploited the topology quite well in order to obtain these advantages. So then we performed the sensitivity analysis, and the dimension were varied using Gaussian probability function, and standard deviation was equal to 8 micrometer for the worst case error of 20 micron, and the number of iterations performed were 100, and the manufacturing yield obtained for this device was 84%. Here we can see the tolerance analysis of the device. Then the device was fabricated with computer control milling, and the material used was aluminum, and the prototype was fabricated in 2 pieces, which we can see here in this photograph. Excuse me. So the final frequency response of the filter was given here, where we can see that both the simulated and measured responses are in good match. And here we have another response with constant width, where we have a low pass response. So here we have the conclusion. So filters with high fabrication tolerances are key to reduce fabrication cost. These robust devices can be fabricated with low-cost milling process are possible with 3D printing. We discussed 3 examples with 3 different topologies. So first was varying height and tapered width topology with 3D printing process, and it has a fabrication yield of 94%. Then we discussed varying height and constant width topology, and the fabrication process was milling, and it has a yield of 92%. And finally, we discussed a varying width and varying height topology, and the fabrication the process was milling, and its fabrication yield was 84%. Thank you.
Okay, thank you, Abdul. We have 4 minutes left. Does anyone have some questions for Abdul? Okay, Reinhard first, you can go.
Okay, thanks very much. Thanks for the presentation. I just was wondering, you said you made the sensitivity analysis, and as I understood it, you had a Gaussian probability function that over